So the thing that we saw in the simulation was that the buoyant force equaled the gravitational force. So what we knew in advance of today was that the weight force and the mass have a relationship. And what we saw today was that the buoyant force and the change in volume have a relationship. And if we're going to keep things equal, then the thing that the weight force has going for it has to come into contact with the thing that the buoyant force does, and the thing that the buoyant force has going for it has to also be in parity with that. And when we rearrange all of that, we just get back that these fancy forms of one, mass is independent of the buoyant force, change in volume is independent of the buoyant force. So we have our law-making scheme on display there. So now what we do is we want to start getting things into the relationships that we observe, or known relationships. So buoyant force, it's what I want to know the structure of, so I'm going to leave that alone. Like we saw at the beginning, the weight force is in some relationship with the gravitational weight force, so I can write it that way. So I'm really just taking this right here and popping it into that. And then I know that mass and volume have a relationship. So all I'm doing now is taking mass in relationship with volume and writing that there. And what's left over is this the change in volume that we observed. So what did we notice is that the buoyant force, at least the way this is written right now, is directly proportional to those three factors. The first factor is just what we call little g. The second factor is density, it's mass per unit volume. And that last factor is volume. So the buoyant force is directly proportional to the force of gravity, the density of the medium, and the change in volume that's observed. And so every time, even in the sinking condition, this will work out. And so really what this boils down to, ultimately, what you'll find typically in the textbook, let me be clear here, is that this density thing is the density of the thing that changed volume. In this case would be water. And so your classical buoyant force formula is just what they call rho GV, but the density of the medium, the volume of the medium, gravity, and the volume of the medium. That's typically the way you'll see the buoyant force used. And you might remember Archimedes' principle. He's a famous Greek dude who, the king said, "Is my crown real gold," or whatever. And he figured out, sitting in a tub, that the way he could determine whether that worked would be on how much it displaced. And so we have that going for us. So that's one way to look at it. Now, to look at things a little bit different, so I'm going to attempt to draw a cylinder. There we go. Not bad. And if we fill this thing up to let's say here. And so this would be this top of the column of water or fluid or whatever. We'll call that area 1. And there'll be uh, a height associated with this. Call this height 1. And we could have our thing there. Call that area 1 on top there. So we know prior knowledge, density is just going to be the mass of this uh, area over the volume. And we know that since it's a cylinder, that a volume would be the same as area 1 times height 1. Area of the base times the height gives us the volume of the cylinder. And this will just lead naturally to mass 1 equals density, area, height. Okay? So if we were to increase the volume of this area, or this in this cylinder here. So now I'm going to add some additional water, same stuff, and this will be area 2, and it'll be associated with a different height, and still the same stuff. So density now is going to be mass 2. Let me switch colors here just for consistency. So mass 2 over volume 2, and this will break down in the same way. Area times height, and leave me with mass 2 is density, area 2, height 2. All right. Okay. So if I want to know what's the force, in other words, what would it weigh? Each column of water, what would it weigh? So we could just go, all right, the force of column 1, or its weight force, would be mass 1 times g, and that's just going to be density, area, height, g, and then F2 would just be mass 2g, and that's going to have the same structure, density, area, height, times g. Now, pressure. We define pressure to be force per unit area. All right? So that means pressure 1, if I just call that P for pressure, is going to be force 1 over the area 1. And of course, that's just going to give you density, gravity, height 1. And if I do pressure 2, then it's going to be force 2 over area 2. So the area is going to drop out. And again, I get density, gravity, height 2. So the change in pressure, if I subtract the big one from the little one, I get this density, gravity, because those are the same in both cases, and going to be a change in height, or height 2 minus height 1. So this is what's the pressure change for the height of a column. So in either case, I can just calculate the pressure of a static column, 1 or 2, and it's going to be more height means more pressure. So if we had a cylinder with a pressure gauge or a weight gauge on the bottom, we could notice this effect easily just by add more water, the weight goes up. It means the pressure goes up. And if we were to put you on the floor and then everyone start laying on top of you, you would feel the pressure increase, the force per unit area, surface area of your body, or 1/2 of that surface area. So this is what they call the pressure fluid height equation. Pressure fluid height equation. I do want to point out, though, that right here, where I have force 1 equals this density area height thing, that area times height is volume. So isn't it the case that I just have density, volume, gravity, and force 1 equals that? Didn't we just find that buoyant force equation? So this, looking at a box of water from a different perspective, we get back the same thing. Of course, we weren't looking for a buoyant force, all right? But basically, what is it telling us? This is telling us that the buoyant force displaces an equal mass. That when something floats, it's because it displaces the weight of the water displaced equals the weight of the mass. Or so basically, whatever chunk is sunk, that mass equals the mass of the water that was displaced. Okay, so we can, when we bring pressure fluid height together with the buoyant force, that's how we come to that conclusion. That's what you'll read in any book, is the mass of the fluid displaced equals the mass that was sunk, so to speak, in the floating condition. All right, so we get back the buoyant force from that analysis.